welcome everyone to today's WiDS Datathon workshop series. I'm Valerie Elliott, the program director for the WiDS Datathon competition. We're so glad to have you all here with us today. This is the third workshop, so the last workshop in the series led by students Kylie, Caterina, and Leah at the University of San Francisco. Today they will be guiding you through how to build and evaluate your machine learning model. So just a couple of housekeeping things before I turn it over to today's instructors. If you can please keep yourself muted while our instructors are speaking, that would be much appreciated. And if there's time at the end, we will take some Q&A. So please use the chat feature to drop your questions in for the instructors. All right, I will turn it over to Kylie, Caterina, and Leah to introduce themselves and get the workshop started.
Hello, I'm Kylie. Sorry. I'm a data science student. I'm a third-year data science student at the University of San Francisco. And I've really enjoyed helping WiDS with the workshops and tutorials for this 2025 Global Challenge.
Hello everyone, my name is Caterina. I'm a second-year data science student, and I'm really excited to be helping with the WiDS Datathon 2025 this year.
Hi everyone, my name is Leah. I'm a second-year data science student at USF, and I'm also a global ambassador of WiDS. And today we are presenting the final workshop of our Datathon series. So let's get started with our workshop outcomes. So in this workshop, we will be going over how to build a multi-output model. Then we will cover how to enhance this model through feature selection. And in this way, we will learn about how to select certain features in order to reduce dimensionality and simplify our models. And then we will also be discussing how to evaluate the model. This will be done through the cross-validation of our training data set. And then lastly, we will be explaining more about the F1 score, which will be used to determine the leaderboard of the Datathon. So before we get started, let's have a brief introduction to what WiDS is and what the mission of WiDS is. It is to change the field of data science across the globe by elevating, educating, and empowering women to achieve 30% representation of women in data science by 2030. And furthermore, to give just a brief challenge overview, this Datathon challenge again aims to answer this question: what brain activity patterns are associated with ADHD? Are they different between males and females? And if so, how? And also to work towards the answer to this question, participants will be tasked with building a multi-outcome model to predict both an individual sex and their ADHD diagnosis using functional brain imaging data of adolescents and their social demographic, emotions, and parenting information. And the participants will be tasked to build a multi-outcome model, which is designed to predict multiple target variables simultaneously using a single machine learning model. And now I will be turning it over to Kylie to talk about how to build the multi-output model.
Thanks, Leah. And one more note about the challenge task is that we will be building a multi-outcome model to predict two target variables, these being gender, female or male. And we're going to have ones be the yes answer and 0 being the no answer. That's just some regular computer science binary. And so for 1, yes, the patient is a female, 0, they are not. And 1, the patient had an ADHD, and 0, they do not, or the model predicts that they do not. So a machine learning model is a mathematical model that, trained on a data set, can make predictions or classifications on new data by identifying patterns within the information. So during training, the model processes input data, which in this case scenario is our X-train or our feature variables, and makes initial predictions, and then which are then compared to our actual known outcomes of our training data, which is our training solutions that you can find on Kaggle, and we will make this our Y-train. And then a learning outcome, such learning algorithm, such as decision trees, helps refine the model's parameters. Decision trees is a tree-like model that splits the data into branches based on feature values, making it easier to interpret and visualize. The decision tree starts with the root node that represents the entire dataset, and then it selects best features to split on, based on criterion like information gain. The dataset is recursively split into branches based on feature values, creating decision nodes. And then once it reaches a stopping condition, such as reaching maximum depth or when further splitting does not increase accuracy, the node itself becomes a leaf, representing a final decision or prediction. And then once your model is trained, it can generalize what it learned from this algorithm and make informed predictions on new data, which is going to be your X test data. And then you will put that into your model and come up with your own solutions, which you will submit on Kaggle. But it's a little bit different for this challenge because we are going to use a multi-outcome model to predict both target variables simultaneously. And this type of model is designed to predict multiple dependent variables or outcomes at the same time rather than one at a time. And for this task, our Y-trained data set will include 2 target columns, gender and ADHD diagnosis. And you might be wondering why we want to use a multi-outcome model for this challenge. But this approach is particularly relevant to our specific challenge, going back to the challenge question that Leah was talking about of investigating ADHD diagnosis in women. And so research suggests that women with ADHD are often undiagnosed. And by modeling gender and ADHD diagnosis together, we can explore potential relationships between these variables. And using the same feature variables to predict both targets allow us to examine this connection in a systematic way. A multi-outcome model is ideal for this purpose because it efficiently handles simultaneous prediction of both variables while leveraging any potential interdependencies between them. And another benefit of the model is just generally that it can be more efficient and it can streamline your workflow. So data preprocessing, model fitting, training, and testing only needs to occur once to predict 2 variables. So you can see how that can be more efficient. So now I'm going to take you guys off of the screen, the presentation, and we're going to head to our notebook instead. So this notebook is accessible to you guys. This is a Jupyter notebook. And we use this notebook for our previous workshops as well. And you guys can watch those previous workshops if you haven't already. But for now, I'm going to show you guys how to actually implement your machine learning into code. So for any machine learning model, you need an X-trained data set, which contains the feature variables used to make predictions about the target variables. In this case, the target variables are ADHD diagnosis and gender. And our feature variables include categorical columns, quantitative variables, and functional connectome matrices. Our first workshop fully went over all of our different variables that we use. So if you need a little bit more explanation on that, you should go back and watch that workshop. And we have prepared our X-trained data frame by encoding categorical variables, merging data frames, and handling missing values by filling NAs. That's all what our second workshop was about. So again, if you need to go back and look at that video after this workshop, you can do that. It can be found on Kaggle. So in addition to our X-train, we also need a Y-train. These are our solutions, the data set containing the target variables to train the model to be able to recognize its patterns. And the target variables allow the model to learn the patterns of the feature variables that lead to specific outcomes for ADHD diagnoses and gender. And this relationship is what enables the model to make accurate predictions when applied to the new data. So the first step that we will take, so we already have our X-trained data set loaded into this notebook because that's what our second workshop was about. But we still need to load in our Y-train data set. And this is the training solutions file that can be found in the training folder in Kaggle. And you can just easily load that in. And then one important note before we get into actually building our model is that both X-train and Y-train datasets, actually all of our datasets, include something called a participant ID. So this serves as an identifier for each patient. And this column is basically just a label for each patient. So it doesn't really have any more information that we want to help predict ADHD or gender. And also it is a categorical data and models only take in answer floats. So before we start training, we are going to drop that column for both our X-train and our Y-train. So now we can actually get into modeling. There is a bunch of models out there that can be used within Python. So we encourage you guys to research on your own and try to figure out what model could work best and optimize your predictions. But today we're going to be demonstrating an XGBoost, which is short for extreme gradient boosting. And it is an optimized implementation of gradient boosting, a machine learning technique that builds an ensemble of decision trees, which I explained a little bit earlier, to make predictions. And it is widely used for structured tabular data, and it is especially popular in competitive data science, like this Kaggle competition, due to its high performance, speed, and flexibility. XGBoost builds an ensemble of decision trees in a sequential manner where each tree corrects the errors of the previous one. The final prediction is the weighted sum of the predictions from all the trees. And gradient boosting means that each tree tries to minimize the error from the previous step by fitting the gradient of the loss function. This iterative process improves the model's accuracy over time. And ensemble learning is by combining multiple weak learners or shallow decision trees. XGBoost creates a strong predictive model. So first step in actually building this model is to create an instance of the XGB classifier from the XGBoost library. So we have a couple import statements here to get those XGBoost classifier and the multi-output classifier. And when we create this base classifier, or we initialize this base classifier, we have a couple parameters here. So objective equals binary or logistic specifies the type as binary classification. So like I said before, our questions here have 1 or 0 answers. So that's a binary question. So again, like 1 for female, 0 for male. That means that it's a classification problem. And n estimators equals 100 sets the number of boosting rounds, or the number of trees to train the ensemble. Learning rate equals 0.1 determines the step size. Shrink is used to prevent overfitting, and lower values result in slower learning, but can improve accuracy. And a little note on that, if you were to download this IPYNB file on your own and try to run it, it will take a few minutes, maybe even more than a few minutes, because we have a large data set and models take a long time. And some of the other steps we take also will take a long time to run on your computer. So let it run for a second, leave it be, and just know that it should take a while. And then max depth equals 5 limits the depth of each decision tree to also prevent overfitting while ensuring the model captures enough complexity. Next, we are going to wrap the XGB classifier with multi-output classifier, a utility from the Skylearn that enables the model to handle multi-target classification. So that's what we're aiming to do in this challenge, is to make that multi-output model. And it is needed because usually XGB classifiers only handle single target classification. So we're going to wrap that multi-output classifier, the XGBoost classifier, with a multi-output classifier. Next, we're going to train that multi-output classifier on the feature matrix X train and then multi-target labels Y train. And how this works is that the multi-output classifier internally splits the Y train into individual target columns. And for each target column, it trains a separate instance of the XGB classifier using the features from X train. So like it says here, it took 6 minutes and 45 seconds to run. So yes, that's just because we have a very large data set and it will take a while to run on your computer. So like I said before, once you have a trained model that has been trained to like recognize those patterns in the feature variables that predict the target variables, now we can actually test it with new data and make our own predictions. So we are also pre-processed our testing data the same way we did our training data. So that's an important note that we talked about in our second workshop, but whatever pre-processing you do on the training data, you're gonna wanna do the same thing to the testing data. So if you encode the categorical columns in the training data, you're gonna wanna encode the columns in the testing data. However you impute NAs in the training data, you're gonna wanna do the same in the testing data. And just like we did for the training data, we're going to drop that participant ID for our testing data. But as you see here, I store that value so that we are able to use it later, because when you submit your actual answers, you want that participant ID there to identify which patient you're predicting for. Then you actually create that instance of Y predictions, and you say multi-output classifier dot predict, and you put in that X test data set that also we built in the second workshop. And that's where this line is what makes our predictions. But we actually want to create like a data frame of these predictions to make it simple and easy. And this is what you will be submitting on Kaggle. So you make that data frame of both the Y predictions and you name your columns, and then you concat back that stored participant ID, which all should align nicely because we stored it as the test DF's participant ID. And once you have that concated back, you have this nice data frame that this is what your submission to Kaggle is going to look like. Obviously, there's many more rows than this, but you have your participant ID and you have your 0 and 1 values for both the predicted gender and the predicted ADHD. So this is, again, just another example of what you're the expected result that you're going to submit on Kaggle. So once you build your model and use it to make predictions, you don't want to just submit this right away to Kaggle. You want to make sure that this is like relatively accurate. And one way we can do this is using cross-validation. So I'm going to go back to the slides and talk a little bit about what cross-validation is. So the cross-validation score is a metric-based used to evaluate the performance of a machine learning model by testing it on multiple subsets of the data. And it provides an estimate of how well the model is likely to generalize the unseen data. And so how it does this is that the data set is divided into K equally sized subsets or folds, use set K, and the model is trained on K-1 folds. And this is all on the training set. And then it is evaluated on the remaining fold or the validation set. And this process is repeated K times with each fold being used once as the validation set. So you will get K different CV scores, and you can average those together and see generally how well your model is performing. And you get to decide the evaluation metric that you use for your cross-validation. We will use accuracy score computed for each iteration. An accuracy score is a simple, what's the Y per actual value minus the predicted value from the model. So it's a simple metric that we will use for cross-validation. You might be wondering why we're using cross-validation. There's many other metrics out there to evaluate a model, but this one's useful because you guys will not have the, true labels for the test data. Of course, that's what you're coming up with, so you're not going to get the test solutions. So this cross-validation is an easy way to evaluate your model only with the training data and the training solutions, rather than with the testing solutions. And cross-validation provides a reliable way to evaluate our model's performance using the training data without needing that testing set answers, and ensures that it is evaluated on multiple subsets of the data. So you don't want to just have, two folds there. It's nice to have multiple folds so that you're doing this multiple times. So let's go back to the Jupyter Notebook. So we can actually see how we're going to implement this into our code. So again, you're going to need to import some libraries from the Skylearn library in Kaggle. So like cross-validation score, make score, and accuracy score. But this all comes from that same Skylearn library in Python. So you might have seen cross-validation before, but when we are using a multi-output model, it's a little bit more complex than a simple two-line of code. We actually need to define a function that converts the y true and the y pred. First thing to do is to convert it into an NumPy array so that it has indexing like this. Where you see the brackets here and the colon and then the I. That's just like for indexing. And then it's going to iterate over each column or target variable in the y true and the y prediction, and computes the accuracy score for each target variable using that accuracy score that I talked about earlier and the accuracy score that you imported here. And it's going to return the average accuracy score across all target variables. So that's why this function is needed for a multi-outcome model, is it computes multiple accuracy scores for both target variables. And then we're going to wrap our multi-output accuracy function into a score object that can be used with scikit-learn's evaluation tools, or like cross-val to get our actual cross-validation. And this will automatically create our y true and our y predicted that's going into this function here, that are parameters for this multi-output accuracy function. So you're going to create that score using this scikit-learn's make score. And then we can actually now perform our cross-validation with our multi-outcome machine learning model while using our X-train and Y-train data frames. So there are the parameters there for the cross-validation score. You put in that model, you put in your X-train, your Y-train, and then CV equals 5 here means that there are K equals 5, what I was talking about before, or there are 5 different folds. So it will iterate over 4, then evaluate on the last one, and it will do that 5 times. And then scoring equals multi-output score. That's where this multi-output score and this function comes into play, so that it can use that custom scoring function for evaluation. And as it notes here, this takes 12 minutes to run this cell. This takes even longer than the actual modeling. And just again, because we have such a large data set. And so just be like patient with it and don't think that it's like an issue or anything. And then you can print out all your CV scores here. And so you're going to get 5 of them, or however many you choose for CV equals, you're going to get different ones. And then of course you can mean those together to get the average. And as you can see here, our CV score initial one was only like 65%. And as you probably can recognize, that's not a great, model if our cross-validation score is only 65%. But there's a couple reasons for this, and this is actually quite expected from me and Caterina and Leah, because First of all, in our second workshop, we showed you guys how to fill NAs with the mean of the column. And while that can be effective and pretty simple to produce, it isn't always the best way to fill NAs or impute your NAs in your values. So that's something that's very challenging about this global challenge, is figuring out how to impute those NAs. And a second reason why this value is not that great is because our data set is very large. So after encoding our categorical variables and also like having all the functional connectome matrices, we have a ton of columns, and also like our quantitative variables. And some of you may know that a model doesn't always predict as well when you have like a super large data set with a bunch of like a super wide data set, so a bunch of columns. So I'm gonna pass it on to Caterina to talk about something called feature engineering, which allows us to minimize the amount of columns while optimizing the model's performance.
Okay, so as Kylie said, feature engineer is the process of transforming raw data into features that are suitable for machine learning models. And in other words, more easier word, is the process of selecting, extracting, and transforming the most relevant feature from the available data to build more accurate and more efficient and also better performing machine learning models. The success of like machine learning models, in our case, our machine learning model to predict ADHD and sex, heavily depends on the quality of the feature used to train them. That's why feature engineering is so important, and feature engineering involves a set of techniques enable us to create new features, transform new feature, you know, get rid of some features by combining and transforming the existing one. These techniques help to align the most important patterns and relationship in the data, kind of going back to like the whole concept of correlations that we explored in the last workshop with exploratory data analysis, which in turn helps, and discovering this relationship and correlations helps the machine learning model learn more from the data and in a more effective ways. So first of all, what is a feature? I did not cover that. So feature in the context of machine learning is also known as variable or attribute, and is an individual measurable property or characteristic of the data point that is used as an input for the machine learning algorithm. Features can be numerical and categorical. We've seen that. We have like categorical data, we have quantitative data, which are numerical, and they represent different aspects of the data and are relevant for like the problem. So in our case, in our data set, of course, the features would be like demographics, characteristics, age, and things like that. So what are the processes involved in feature engineers? So first of all, we have feature creation. Feature creation is the process of generating new features based on domain knowledge and by observing pattern in the data. And it is a form of feature engineer, of course, like it will improve the performance of your machine learning model. So there are different types of feature creation. Of course, most of the feature creation requires domain specific knowledge. So I would definitely recommend, before going to that route, to like explore more all the resources that we have in the Kaggle page about ADHD in the youth, and now that it shows up different sex and like maybe something about like neuroimaging. I will read a lot of research articles before going to actually like creating new features, especially if you're not an expert in the domain itself. And then, but it also, feature creation can involve data-driven decisions, so creating new features by observing patterns in the data, such as calculating aggregation or forming interaction terms between two features. This goes back to like the correlation concept of like, if two variables, two features are really correlated, you want to like form an interaction term to just make that relationship stronger in predicting the model. Then we go into feature transformation. So feature transformation is another process involved in feature engineers, and is the process of transforming the features into a more suitable representation for the machine learning model. So we can have normalization, rescaling the features to have a similar range, such as like between 0 and 1, to prevent some features from dominating over others. especially because we have such a different like data types. We have categorical and then we have also quantitative. You want to use, like, we're not going to go over this workshop how to use numerization, but you can use that. And you can make all features between all the values between 0 and 1. Something that also is part of feature transformation that someone mentioned in the chat before, it's scaling. Scaling is a technique used to transform numerical variables to have similar scale, so they can be compared more easily. We're not gonna go over this in this workshop, but feel free to research it because really can improve the performance of your model. Encoding. So encoding actually is part of feature transformation. It's something that we already went over, or at least Kylie went over in the second workshop. And we did that for, to transform categorical feature in numerical representation to better our machine learning model. So if you're interested, please check out the last workshop that we had where we went over what encoding. Okay, next process involved in feature engineer is feature extraction. So it's the process of creating new features from existing one to provide more relevant information to the machine learning model. So types of feature extraction are dimensionality reduction. So that means like dimensionality means like how many variables, how many features you have, you want to reduce those, and you want to transform the data into a lower dimensional space, so have less features. And so the machine learning model is simpler and can provide a better outcome. Feature combination, so combining two existing features. For example, again, an interaction term between two features. You can also use feature aggregation, aggregating two features in one for like, or for example, calculating a set of feature mean, sum, or count. Feature transformation again. And then another process is feature selection. We're gonna go actually over feature selection in this workshop, but it's the process of selecting subset of relevant features from the data set to be used in the machine learning model. Last process involving feature engineering is feature scaling. Again, feature scaling is really important. Someone mentioned it before, but it's the process of transforming the features so they have a similar scaling. So there are different types: min, max scaling. So like recalling all the features, scaling all the features in a range between 0 and 1. Standard scaling, so everyone has a standard deviation 1. Robust scaling, there's a lot of type of like feature scaling. I know this is a lot of like new, especially if you're just starting out with data science, a lot of new vocabularies and concepts. So please don't be scared of, like, if you are interested in any of these things, please feel free to research it. We're not gonna go over each of these processes, but you can definitely feel free to like research. There's many more out there. Yeah, don't be scared. Also, this challenge is also about learning. So if you're starting out, this is a great way to like get like familiar with some terms. So yeah, can we go to the next slide, please? Okay, so what is feature selection? So again, feature selection is the process of selecting the most consistent, non-redundant, and relevant feature to use in the model construction. And the main goal of feature selection is to improve the performance of a predictive model and reduce the computational cost of modeling. So computational cost means like, as we've seen, like the model that Kylie's fitted before took like literally 5 minutes, right? That's a lot. That's a lot of computational time cost. So you want to reduce those costs. Also, feature selection is one of the main components of feature engineers, again, as I said before, and is the process of selecting the most important feature to input in machine learning model, right? And then feature selection techniques are employed to reduce the number of input variables by eliminating redundant or irrelevant features, as I said before. How we do that? One way to do it is like exploratory data analysis that we went over in the last workshop. You want to see what variables have a greater correlation with the output that you want to see, so like sex and ADHD, right? So the many benefits of, just list some benefits of what feature selections are for, but there are probably many more, but these are like the main ones. So simpler models are more simple. A model that is too complex is unexplainable, and it's not really valuable, especially in like research, like in our data set. Like, you want to be able to explain what are some relationship between ADHD and sex, and all the variables that we have. And then we have shorter training times. As I said before, the model doesn't take as much time to train. Variance reduction, so increasing the precision of the estimates that can be obtained for the given simulation, especially with a like such noisy data set as we have. Like, you wanna try to reduce their variance. And then you want to last benefit is to avoid the curse of high dimensionality. So what is the curse of high dimensionality? So dimensionality phenomenon is just dimensionality is like, and the number of features, so as dimensionality and the number of feature increases, the volume of spaces increases so fast that the available data becomes limited. So to like just put in simple terms, when you add more features or dimensions to the data set, features or dimensions, the space where the data set becomes like much bigger and much larger. So think about it like adding more direction where you can move in. So you know, every time for each data point, you can move in different directions. So because you have so many features, right? In our case, we have 20,000. So as you add more direction, more feature, the space expands quickly and the data points like spread more apart. So it's really hard at that point to aggregate points and like kind of like analyze patterns. And this means that even if you have like a lot of data points, they're like so spread apart that it becomes harder to find meaningful partners or like make accurate prediction. So yeah, so feature selection algorithm are characterized as supervised, unsupervised. Today we're gonna go over logistic regression for feature selection. And we chose logistic regression. If you can go to the next slide, Kylie, thank you. Because we have a classification problem with whether participants have ADHD or not, and whether the sex is female or not. So we have a binary outcome, right? Yes, no, 1, 0, based on and so it's logistic regression is widely used in classification problems. So why use logistic regression for feature selection? Again, logistic regression not only predicts outcome, but it also provides useful information about how each feature affects the prediction. So logistic regression does not only predicts, but also gives us information about which variables are the most important in predicting variable, right? And gives us coefficients. So there's two, again, there's two how does logistic regression help in feature selection? We have coefficients, so each feature in the model has a coefficient that indicates how strongly the feature is correlated to the outcome. And then we have also regularization. We're gonna use both. So regularization is using L1 regularization can further improve feature selection by shrinking less important feature coefficient to 0. So we can go to the next slide. So an important concept actually, it's also like, this is a recursive process, right? The idea behind feature elimination, feature selection is that it's a recursive process. The first time you're gonna eliminate get rid of some features, and you're gonna measure how good your model is, and then you're gonna wanna go back to your model and like take away some feature or like add some feature. It's an iterative process. You're gonna have to repeat this process many times before getting a really good performance score, right? So there are two ways to implement logistic regression using coefficients. Again, you feed the model, you train a logistic regression model, you extract the coefficients, get the coefficients of the model, and the absolute values of the coefficients indicate the importance of the corresponding feature, and then you of course select the highest absolute coefficients. And then for using L1 regularization, you use one L1 penalty. So you train a logistic regression model, and as how L1 regularization works is that it tends to shrinks like all the coefficients or like the less important coefficients to 0. So all the values that are non-zero coefficients, all the features that are non-zeros, they end up they be the important ones. So yeah, now we can switch over to the Jupyter notebook and kind of look at the code. Thank you. So again, we're gonna start by using the coefficient technique. So first of all, we're gonna import logistic regression model from the sklearn library, and then we will first look at the feature selection only for the sex target, right? Because we have two targets. Again, this is really particular challenge because we have a multi-outcome model. So you want to see which variables are important in predicting sex and which variables are important in predicting ADHD, and then combine them together, right? So I just feed creating feed a logistic regression model where we pass as an argument max either 1000. We just set the maximum number of iteration to be 1000 just to be able to run it in a reasonable time. I think it takes like 2 to 3 minutes to run this. And then we then feed the model. We feed the model by making sure that we select the train outcome, the sex, right? And then once we fed the model, we extract the coefficients. As you can see, we extract the coefficients. They're important for sex prediction. and by also just dropping the participant ID because we don't really care about that column, we identify the top features. In my case, I took the absolute values of all the coefficients and I selected the first 10, right? And then those are just like the most predictive one. But you can definitely, there's way more. And then I just plot a visualization, if you can scroll down, to just plot some of like the most important features for sex outcome. Again, you can see some categorical, most of them are also like brain regions, which is pretty cool. Something to like look more into it. So next we went over looking at coefficients from logistic regression for in predicting ADHD outcome. So again, we fitted the model, same process. We selected the ADHD outcome with we selected all the coefficients, the top 10 coefficients, the absolute values. And again, we can see some similarities, some things that like show up again, some kind of like demographics variables. So we actually plot it again. And we can definitely see some similarities between things in things that are important for predicting ADHD and things for important in predicting sex. So next, if you can scroll down, so now we're gonna use L1 regularization, which is another type of that we can use for logistic regression. Again, we're gonna fit a logistic regression model, but this time we're gonna pass on as an argument penalty L1, and as a solver linear. And then again, linear just refers to optimization algorithm used to solve the logistic regression. So at that point, we just select all the variables, as you can see in the code. They are different, all the coefficients are different from 0, right? Selected feature train df drop different from 0, model coefficients different from 0. So those are all the columns, right? And then next, we will now use like L1, and then once we have those variables, we do the same thing in predicting ADHD, because before it was just for sex. We get those features that are important in predicting ADHD outcome. So next, what we actually talked about is fitting the model, right? Once you have what are the most important features, you want to fit a model, or you want to try. This is just a first try. Of course, as I said, it's an iterative process. So we're gonna go in the next step. So row selection reduction to improve the model. And then, so we, no, if you can, yeah, that's great. And then first we can define the train and test. We want to find the common features between ADHD important feature and sex important feature. We select the set function because set makes it easier to find common values, and it returns only the values that exist in both sets, and we make a list of it. We form the X-train X-test by just selecting the columns that are important both for ADHD and sex. We fit again what same thing that Kylie went over before, but we fit a multi-outcome model, XGBoost classifier, and a multi-outcome classifier. We fit that with X train and Y train. In this case, the X train 2 because it's a different train, right? We just selected some features and we got rid of some others. So we get the prediction, the Y prediction. That's like the output you wanna see and you wanna send in Kaggle. If this is a good, of course, if this is a good enough model for you. And then at this point, we're going to go into evaluating the model with cross-validation scores. So as you can see, we imported again, same thing Kylie did before, same function. We perform the cross-validation score on the training data, and we get the mean of this 5 folds value that we get from this cross-validation, this 5 performance that we get the mean, and the mean is 0.672, which is definitely an improvement from the 65 that we got back in the first model. I'm definitely aware that this is not the best prediction ever, and there's definitely so much more to improve, and improvement is going to be slow because you want to like select and select and get rid of some variable, of some features, and it's an iterative process again. And that's like why feature engineering is so important, and it's not just a one-step process, but it's just you going back to it, adding some interaction terms, domain-specific transformation, feature importance analysis. It's a really like coming back to the model, fitting the model, evaluating the model, going back to feature selection. It's a iterative process again, as I said, and there's so many like statistical like methods and things out there that you can research into. Those that I mentioned are not all the only one they're out there. feel free to research and apply what works best for your model. And now we're gonna pass it over to Leah.
Okay, so now we will be talking about the F1 score, which will be the evaluation metric that will be utilized in order to determine the performance of your model. So this will be the metric used to see who is leading the leaderboard of our datathon. And the highest possible score in the F1 metric is 1, while the lowest is 0. So a score of 1 means that both precision and recall are perfect. And today I will be explaining two parameters, namely precision and recall, and how it plays into the F1 score and how it's both precision and recall are combined to make the F1 score. So yeah, I will be explaining the relationship between the F1 score and machine learning and these two parameters. And again, just a reminder, since we are working towards two target variables, one is for when an individual is predicted to be female, while 0 for male. And then on the other hand, 1 is for when an individual is predicted to have ADHD, while 0 is when they're predicted to not have ADHD. So first, what is precision? Precision indicates the proportion of true positives among predictive positive cases. In the case of our datathon, this indicates the ratio of individuals truly diagnosed with ADHD among the predicted diagnosed individuals. More specifically, as you can see in this in the equation that's right in front of you, this is the ratio of diagnosed individuals among those who were predicted to have ADHD, both true and false positives. And then for the sex aspect, this is a proportion of female participants among the number of predicted female participants. So again, precision is just true positives over the number of all predicted positives, whether or not it's a true positive or a false positive. And then following this, what is recall? Recall, on the other hand, indicates a proportion of true positives among all actual positives, including the false negatives predicted by our model. So in our case, this is the ratio of diagnosed individuals among those who are truly diagnosed with ADHD, both the true positives, so those are the correct predictions, and false negatives. And then for the sex aspect, this is the proportion of female participants among the number of actual female participants. So for context, recall can be much more critical, especially in our context of maybe like a medical diagnosis, since high recall indicates fewer chances of false negatives about a certain diagnosis or illness. And then following this, both recall and precision are then combined through something called the harmonic mean. So what is the harmonic mean and why is that the metric? The harmonic mean combines these two factors in order to determine the F1 score. Precision measures the accuracy of positive predictions, while recall, on the other hand, measures the ability of your model to predict and or identify true positivity. The harmonic mean ensures that these two factors are weighed together equally or symmetrically despite their differences in the denominator. So as you can see, the F1 score here, this is the equation for it. So it's 2 times the product of precision and recall over all the sum of precision and recall. So since the goal of our datathon is to predict ADHD diagnosis and the female sex, the accurate prediction of the female sex in your model weighs higher. This is because ADHD in general is harder to predict in females. Furthermore, in our implementation of the F1 score, the weighted F1 score is calculated on each column separately. So the F1 score for the sex category and also the F1 score for the diagnosis, the ADHD diagnosis, are computed separately in 2 separate harmonic means. And then those 2 individual scores are averaged to get the final Kaggle leaderboard score. So yeah, that is the F1 score explained. And then just to reiterate our timeline, since this is our last Datathon workshop, so the first deadline has already passed, which is the start date. So registration already opened last January 7th. April 16, which is in a few months, the leaderboard prize form opens. You just have to fill out a brief form for you to be eligible for the prizes. And then on April 27, the last day for participants to join or merge teams. And then April 30, this is the final submission deadline, and also the prize form also closes at that time. And then May 7th, of course, the winners are announced, and the top performance may also be recognized throughout the competition, and all deadlines are at 11:59 p.m. Yeah, that concludes our workshop. Thank you so much.
Thank you so much. What a comprehensive workshop. Very well done. And we hope that you all gained a lot of knowledge and insight from today's session. So let's see, are there any questions? If you have any questions for Caterina or Kylie or Leah, please put them in the chat. Thank you, Caterina, for already addressing some of these. Are there any questions at the moment?
Yeah, I saw a question. I think Nicholas asked it, Nicholas Smith, about inputting using mean can add bias into the data set, and since the classes are imbalanced towards males, the model will perform poorly. And one solution that Nicholas gives to this problem is like filter the data set and have two subset, one for male and one for female, and then input these two subset and combine them at the end. I think this is a great approach that I didn't think of. So that's a great way to do it. I would definitely go because like that approach like is a good way to reduce bias, as you said, in putting like missing values in an imbalanced data set. Because as you notice, like, and as we said, I think in the first workshop, like there's the majority, or I think we saw in the second workshop, but the majority of subjects in this data set are male. So there's a big imbalance. So by separating the data into like males and female subset before splitting, you ensure that like each group can like retain its like unique distribution in some sense, preventing like the mean imputation for like from like over like represent a group rather than another. And then after like as you said, after like you input it, like you can combine the subset, leading to like a more balanced like and fair model in some sense, and you can probably get a better performance, or at least I would hope. I haven't tried it, but should work, and then you can fit just the multi-outcome model.
Yeah, thank you for clarifying that. Nicola, I hope that helped answer your question and provide some clarity. Okay, good. You responded in the chat. Just to let you all know, I did put the link to the notebook in the chat, and so we encourage you to take a look at the Google Colab notebook that they reviewed today, and you can use that as a resource for your modeling and your work on the Datathon. You can also find all of the recorded workshops from workshop number 1 and workshop number 2, both on the Kaggle page and in the community hub. So I know that was referenced several times today. It's super important to watch all 3 workshops because they build on each other really well. And so if you're looking for some additional assistance or want some review on a prior workshop, you can find those links in those places. Additionally, we will be posting the recording to this workshop as well as the slide deck and the notebook in the community hub and on the Kaggle page as well. So you'll have everything together to work on. I also wanted to mention that there are ambassadors all over the world hosting Datathon workshops to help you with additional support or to help you find teams. And so if you haven't already, feel free to check out the events page on the community hub. I'll post a link to it in the chat, and you're more than welcome to attend any of the workshops. If there's one near you, you can attend. A lot of them are in person, and many are also online. So this is the last of the workshop series that WiDS is hosting, but ambassadors are here to continue supporting you along your Datathon journey. Any other questions for our instructors? I do see lots of thank you. Many thanks for the detailed workshop. Yeah, any other questions? Otherwise, we will conclude for the day and let you get back to your day. Okay, wonderful. The final thing I will mention is it's always fun to see your work on the competition. And so feel free to use the Kaggle discussion forums to share your work, your insights. We always love to see your approach to the challenge. So feel free to post your work there. Well, thank you, Kylie, Caterina, and Leah. It's just been such a pleasure to have you supporting our participants with such engaging and thorough workshops. So thank you for all of the support. And we hope you all have a great rest of your day.
Thank you, everyone.
Thank you, everyone.
Thank you, everyone. Have a good rest of your day.